Operator. My name is Todd Stauffer. I'm the Director of Alarm Management Services here at Exida. Audio for this webinar is via the GoToWebinar application. You should all be muted, but should be able to hear. If you have questions, please feel free to enter them into, there's a questions tool on the right side of the screen. And if we have time at the end of the webinar, we'll either go through them or I will answer them as a follow-up to this presentation. So as I mentioned, my name is Todd Stauffer. I lead up the alarm management business here at Exida. I've been involved in alarm management for quite a while, actually as an editor and voting member for the ISA 18.2 standard since 2005. So that's been quite a while. ISA 18.2 standard, just to set the stage for that, was the original standard that came out. It was then used as the basis for the IEC 62682 standard, which is essentially what is used for the UK. I've also been involved with the review of the EMUA 191 document and other ISA 18.2 technical reports that provide additional detailed information about alarm management practices. My latest task is to be the co-chair for a new standard that is designed to bring together the worlds of alarm management and functional safety. This is a standard on safety controls, alarms, and interlocks. So with that, let's get started. A little bit about Exida. Formed in 1999 to make the world a safer place. And when I say world, I mean process plants mostly. That was functional safety initially, but it has branched out to be cybersecurity and alarm management in the last 5+ years. If you're familiar with us, it's probably because of the references that you've seen to us as an agency of certifying devices. If you've worked with a safety instrumented system or put together one and dealt with equipment that is SIL related or SIL capable or SIL compatible, chances are it was Exida that did that certification. So we also do certification of people to make sure that they are able to carry on the tasks appropriately for the functional safety lifecycle. And we have a suite of software for SIS design and engineering, which as part of that, we include our SIL alarm rationalization tool, which we'll talk a little bit about during this webinar. So in general, contents, what are we talking about? We are talking about nuisance alarms. What are they? What's the dangers of having them? We'll talk about the different types of nuisance alarms, how you identify them. We'll spend a lot of time talking about how to eliminate or minimize them. And we will also spend a significant amount of time talking about human factors considerations of nuisance alarms. For example, how it impacts or creates operator error, and whether operator error is really a root cause of a problem. So let's get started. First, a question to look at and understand the role of the operator in a process plant. So what role in today's society analyzes information, diagnoses situations, predicts outcomes, and takes action to deliver value? Is it an airline pilot, a doctor, an air traffic controller, an operator, or all the above? That's a pretty easy gimme question, of course. And the answer is all of the above. The idea of this question is to get you to see how the operator is similar in their role to, let's take an airline pilot or a doctor. They take in a lot of information, a lot of data, and they need to make quick decisions that affect the bottom line of the operation, or the safety of the passengers per se, or the safety of the patient. So the alarm system is actually a key tool to help the operator do their job, and that's part of what we're going to talk about. So the alarm system is key tool for them to do their job, and alarms are part of that and help the operators know what to do and when. Now, what is the purpose of an alarm? If we look at this schematic of a typical process upset, during normal operations, the distributed control system is pretty much typically able to keep the process in your normal operating range. However, in some cases, you'll have a upset, a piece of equipment will malfunction, change in operating conditions, all kinds of different reasons that the process will start to deviate and go out of the normal operating range into the abnormal area. That is when we want an alarm to occur. And we want that alarm to indicate to the operator that an abnormal situation has occurred, requires their attention, and that it will guide them to take the appropriate action. And if the operator does that, the process will turn around and go back to the green area, go back to the normal operating range. If the operator does not respond or does not respond in time, the process will continue to deviate and go out of the abnormal area into shutdown. So that means a consequence will occur, whether it is truly a process shutdown, an SIS activation, or some other kind of consequence. The idea is if the alarm is not responded to appropriately, we end up in that area. So the purpose of an alarm is pretty clear. If the alarm goes off, and there's very much a direct correlation here. If an alarm goes off, that means abnormal situation, and it requires the operator action. And if the operator takes the appropriate action in the right amount of time, the situation is corrected and the alarm clears. So that's what alarms are supposed to do. But how often do we see that there are scenarios in a process plant where your alarm summary displays are full of alarms, full of stale alarms, alarms that don't disappear, alarms that are there constantly on the console. This is an example showing we deal with alarm summary displays that are full from top to bottom, even continue on to the next page because they're so full of stale alarms. So what we are talking about then is, in this scenario, we are going to talk about nuisance alarms. There are many different issues, or I'll call them alarm management villains, that can rob the operator of the benefit of the alarm system. In this seminar, we're going to focus on nuisance alarms. So let's talk about what a nuisance alarm is, the definition. It is an alarm that annunciates excessively, unnecessarily, or does not return to normal even after the correct operator response is taken. So what does that mean? That means if you're an operator and you have a new alarm that annunciates, chances are you will respond to that appropriately based on your training the first time that alarm occurs. So let's say you take that response and the alarm doesn't clear. It doesn't go away and nothing happens. Then the next time that alarm occurs, maybe you follow the same pattern. But at some point when the alarm occurs, knowing that the alarm doesn't clear and nothing happens, you're going to start to ignore that alarm. And if you ignore the alarm and no consequence occurs, then it becomes fixated in your mind that that alarm is a false alarm or a nuisance alarm. So that effectively desensitizes the operator to that particular alarm, and then in general to all of the alarms from the alarm system. So that's a practice or a mentality that we want to try to prevent. Not only do nuisance alarms desensitize the operator, but they also distract them and make it harder for them to see new alarms. So it can lead to the missing of alarms. Now we've created a Lego video that reinforces the importance of nuisance alarms. Nuisance alarms are not unlike the boy who cried wolf. And unfortunately, we can't show that video during this webinar, but we'll provide the link afterwards. It's actually shown down here. But what that video does is kind of draw the analogy between the boy who cried wolf and a sump pump that generates spurious high alarms in regard to commanding the operator's attention. So the operators are similar to the townspeople. The operator comes out to respond to the sump pump's high alarm, finding that there's nothing that they need to do. They eventually ignore that alarm, and then the sump overflows, of course. So I encourage you to check out that video when we send that link around. Now, one of the connections of that video is it's not just a fable. It relates to a real-life situation in a chemical plant, and which is what inspired it in the first place. So here is that situation. We have a set of pumps, reagent pumps, that are transferring that fluid into a neutralization process area, and those pumps develop a leak. That leak continues, creates alarms both in the sump area and in the neutralization area. The operator focuses on the upset in the neutralization area, trying to resolve what's going on and take care of the situation. So we have a high level alarm in the sump, then we have a high level alarm in the sump, and the operator ignores them, focusing on just the neutralization area. Because they don't have a good understanding of the process, they are ignoring the impact of the sump or the feed area, thinking that because it's a nuisance alarm, or it's been a nuisance alarm, that there's no need to consider it in the terms of the diagnosis and corrective action. So they are not able to correct the process problem. Next shift, a new operator comes on and notices that 10,000 gallons have been spilled into the environment. So we wrote a paper and did an analysis of that, looking at the failure mechanisms. And one of the main problems was that the sump, the way it was designed, the alarming, the high level alarm would go off every time that the pump turned on to indicate that, so it was used as the pump set point as well. So the operator got accustomed to ignoring that alarm. So then when a high level alarm comes from that same area that you've been ignoring, how do you know whether you should respond to it or not? Well, so the operator basically ruled out that as a source, and their attention was tunneling into the neutralization area only. And because they discounted that as the sump area as the potential source, their mental model of the process, their understanding or linking of causes and events was not correct, and they were not able to respond correctly. But it all goes back to the fact that they were presented with high-level nuisance alarms that caused them to ignore that alarm in general. So how did we get into this situation? Well, in the olden days of panel board control, there was a lot of thought and effort put into what points should be alarmed, because there was a real cost and there was limited real estate for that in the control room. When you fast forward to today's modern DCS, alarms are essentially free. They're in software. It's just a simple checkbox to enable a deviation or rate of change alarm or a high alarm without thought about whether they're truly needed or not. And if you're not sure whether you need an alarm, what do people typically do? They would enable it just to be safe. So unfortunately, that has led to an overabundance of alarming where many of the alarms don't have a good basis. So that has led to nuisance alarms. The way we solve that problem, or one of the key ways to solve that problem, is to go back to the methodology or the thought process that we used to use which was for each alarm, make sure we establish what the purpose is and what the operator is supposed to do. Now, in today's world, we call that alarm rationalization, and we'll see how that fits in later. So now let's move on and talk about the different types of nuisance alarms and how we identify them. First type is called a chattering alarm. This is an alarm that goes in and out of alarm with a high frequency, like for example, 3 times in 1 minute. So this can become very annoying. It's a real alarm, perhaps, but the fact that it goes in and out of alarm can be annoying to the operator and can create many events. The other thing about it is it will clear without the operator perhaps even doing anything. So it goes into alarm for a couple of seconds and maybe clears right away. Another similar type of alarm is called a fleeting alarm. It just does not repeat immediately, but otherwise it goes in and out with a short frequency as well. So here's an example of some software as part of the Delta V system that allows you to analyze and capture these chattering and fleeting alarms. So in this report, in this example, we see a couple of alarms identified that have activated many, many times and been active for just a short period of time. This very first one that we see here has activated 50,000 times and been active for an average of 5 seconds at a time. So that means typically that alarm comes in and clears on its own within 5 seconds. So the operator may not have even seen or realized the alarm was there before it's cleared, but it's probably annunciated via the horn and created an interruption to the operator. So you can imagine what this does to your cognitive thinking process. Another type of nuisance alarm is a standing alarm. We characterize it as a nuisance alarm when the alarm has been active for a long period of time, and we'll establish that period as, let's say, 24 hours. We call those stale alarms. Those were the alarms I was referring to earlier, the ones that are always displayed on the console. When you go into a typical control room and you look at their alarm summary display, if you scroll all the way to the bottom, you'll probably find some alarms that have been there for weeks, months, or even years. So obviously they're not serving any purpose, and they are actually detrimental because they are clogging the alarm summary display, making it harder for the operator to see new alarms come in. So again, an example of being able to identify these stale alarms with the idea that we want to figure out what's happening so that we can correct them. Part of what may cause a stale alarm, other than it's just a poorly designed or inappropriate alarm, may be that the alarm setting is not correct for the mode of the process. So if you're making different products, for example, you may find that you get an alarm because it's not set up correctly, and that alarm stays there for the entire time that the operation is in a certain mode. So that can create stale alarms, and we'll talk about how to address that. Now, related to auditing, I wanted to throw in a couple of slides and a couple of thoughts about that. In the UK, the Health and Safety Executive, as part of their questionnaire or toolkit for their auditors, includes information about how well the alarm system is working, including a question about nuisance alarms and whether there are nuisance alarms present in normal or upset conditions. How do you think an auditor would check to see whether you have nuisance alarms? The easiest way is to look at that alarm summary display. And if it is full, then, and the alarms are not changing, and you look at the date timestamp and they have been there for a while, then they know quickly and easily that you have a nuisance alarm problem. So, and we've seen similar scenarios occur in the US from companies that have been audited by OSHA or the FDA or their insurers, where an auditor will come in, not necessarily focusing on the alarm system, but in the control room, they notice the list of all the alarms on the summary display, and they start to investigate. They start to probe into it. And they'll ask the operator that's on shift, what's the purpose of this alarm? What is it for? And what do you do when this alarm occurs? And if it's a nuisance alarm that's been there for 6 months or whatever, what do you think the operator says? Very often they'll say, I don't know what it's for, I ignore it. Imagine what the auditor is going to think if that's what they hear from the operator. So one of the key takeaways from this is that nuisance alarms are one of the easiest alarm management problems for an auditor to detect. So all the more reason why you want to focus on getting rid of them. Another type of nuisance alarm is what we call bad actors. These are frequently occurring alarms. You'll typically find in an unrationalized system that there's maybe 10 to 20 tags that create the majority of the alarm annunciation. So 50%, 80%, it kind of follows a Pareto distribution. So your control system may have 10,000 configured alarms in it, but there may be just 10 alarms that cause 80% of the annunciations to the operator. So you can imagine if you can identify those bad actors, they become the alarms that you choose to fix first and right away to help the operator's performance. So in this example, we can see that there are 10 modules that if we just focus on fixing the alarms associated with them would reduce the alarm activations by 52%. So significant benefit for doing that. Another type of nuisance alarm are redundant alarms. So this relates to the situation where we have one event, one upset, one abnormal situation, and we get multiple alarms. They either occur at the same time or maybe they're slightly time sequenced. It's kind of like a set of dominoes. Once one alarm occurs, it causes another one, which causes another one, which causes another one. That frequently happens when you have, equipment that is interlocked together from a logic or configuration point of view. They're naturally tied together, and when something happens automatically or something is triggered, that results in other state changes, which result in multiple alarms, all essentially indicating the same thing, and that's the problem. So how do we eliminate these alarms, or what do we do? How do we create a program? Well, the IEC standard and the ISA standard have established some metrics or KPIs to evaluate yourself against when it comes to these nuisance alarms. And we can see 3 of the categories that we just talked about. The top 10 most frequent alarms, the bad actors, should be less than 1 to 5%, or on the order of 1 to 5%. The quantity of chattering alarms ideally should be 0. The quantity of stale alarms, and this is an important one, less than 5 present on any day with action plans to address. So that would mean if we're looking at your alarm summary display, those old alarms, you should have no more than 5, and ideally you're trying to get rid of all of them. So that provides some vision to where you need to get to when it comes to resolving nuisance alarms. So now let's change gears a little bit and talk about human factors as it relates to nuisance alarms. So the IEC standard, or the British standard 62682, defines an operator response model. So what does it look like? It's really, you can think of it as 3 different steps. The first step is that the operator needs to detect that the alarm is present. The second step is they need to then diagnose what is the problem and figure out what is the appropriate corrective action to take. The third step is to take the response. And we don't mean acknowledging the alarm, we mean opening a valve, turning on a backup pump, something that will correct the process abnormality. Now, if we think about where those three steps or those three actions can fail and what some of the common failure mechanisms are, we can see that nuisance alarms kind of impact all of those steps. Certainly in the detection step, if your HMI has, if you have nuisance alarms and if you have graphics not created to emphasize new alarms, it can be very difficult to see a new alarm come in. But if you have chattering alarms or stale alarms, that's going to make it hard for the operator to see that there's a new alarm present. So that could delay the amount of time or cause them to miss it altogether. The second step, the diagnosis, the understanding of what's happening, the process model, the mental model, that can get messed up, as we saw, by nuisance alarms, because they can cause the operator to ignore specific alarms, ignore some of those vital cues, and if it's inappropriate to ignore them, then they won't be able to form an accurate mental model. So nuisance alarms impact that step. And then when we look at the third step, the response step, this is typically where we think about operator error occurring, meaning either the operator has not taken any action, call that the error of omission, or they've taken an incorrect action, the error of commission. We typically think about operator error in terms of those two events. But if we look at this and how this process works, is it fair to consider something an operator error, so maybe they make the incorrect action, if the operator is subjected to a poor HMI design, nuisance alarms, has not received the appropriate training on how to deal with the process or understand what the alarms mean? We're kind of setting up the operator for failure if there are nuisance alarms present and we are compromising the detect and diagnosis step. It's pretty easy to see that there would be a problem in the response step. So one of the takeaways of this seminar is about the concept of operator error. You very often hear in incident investigations that are done internally, for example, that the root cause was operator error. And one of the statements I heard at a recent global process safety conference was that rarely is operator error truly the root cause of the problem. And if we look back at that example of the overflowing of the sump pump, that could initially have been labeled as operator error, but that truly wasn't the root cause. The root cause related more to having those inappropriate alarms there. So I caution people to jump to operator error as the problem or the root cause for something until we understand more about what the situation was like. Now, situation awareness is a key element of helping the operator to do their job as best they can. And what is situation awareness? It means being aware of what's happening around you and projecting and understanding what that means to you now and in the future. So that means taking in your external cues, which can be the process data on your HMI graphics, or it can be alarms, and understanding and figuring out what they mean, running that information through your process model, your mental model, to comprehend what is happening now and to be able to project that out into the future as what will happen if you don't take the appropriate corrective action. So what do nuisance alarms do? Well, they're the input here. They're the external cues. How easy is it to develop a good mental model and have situation awareness if you can't even rely on your external cues, if you have to figure out which ones are real and which ones are false? And that's essentially what's happening with nuisance alarms. We're asking the operator to truly understand and respond correctly, but we're giving them false information to begin with. So nuisance alarms can really impact situation awareness. Now let's talk a little bit about alarms and signal detection theory as a way to also understand human behavior. So if we look at these probability plots, we are showing the probability of noise distribution versus a true signal. And what you'll find is that they overlap. And there is a certain point that you set, or effectively gets set, that is the threshold for at what point you consider something to be a legitimate alarm. That would be everything to the right, or is not an alarm, everything to the left. Part of the purpose of showing you this is that it may not really be possible to totally eliminate all nuisance alarms. If you look at this signal detection theory, to eliminate nuisance alarms, we would need to reduce or change where this criterion gets set. So if we were to move it to the right to help get rid of the nuisance alarms, or the times that we detect falsely an alarm, then what's going to happen? That's going to increase the area of a true alarm that we ignore. So in reality, in design of systems, there is a trade-off or a compromise between false alarms and true alarms. So we have to keep that in mind. That doesn't mean that we should not be trying to eliminate as many alarms as we can, though. And what we'll see is that the impact of that is different depending upon workload, actually. So just as a general thing to make sure that we're all on the same page, in general, I think for a typical process plant, your operators are going to have a significant workload, either normal or overloaded. And in that case, nuisance alarms are very detrimental, as well as missing alarms is detrimental as well. But the more overloaded the operator is, the more impactful false alarms or nuisance alarms are. If you look at the other end of the spectrum, if the operator was not overloaded, if they were actually underloaded, then false alarms or nuisance alarms actually may not be detrimental. They may actually help increase vigilance. So what the heck does that mean? What's an example? Well, let's say you're an operator on third shift and you only get one alarm during your entire shift. Well, that's good, but it may cause you to be very passive and not be monitoring as closely the system as you need to be. So for that scenario where you're well below your nominal thresholds, getting a couple of nuisance alarms that re-engage the operator or draw their attention in, and when I say a nuisance alarm or a false alarm, I mean that they would actually respond to it as if it was a correct alarm. That may actually be a good thing. That may increase their attention to the system. But I would say that probably for most scenarios in a process plant, what we're talking about is an overloaded operator. So that would say that nuisance alarms can be detrimental to the operator's performance. So now what do we do with that? With understanding that there is some overlap between the noise and the signal. And when I say noise, I don't necessarily mean only audible noise. I mean noise to the environment of the operator in their ability to detect an alarm. So that could be audible noise. It could be the talking in the background. It could be poor HMI. It could be bad lighting. It could be visual noise. For example, if red and yellow are your colors that you use for alarming, and you're also using that for symbols in your HMI, that is visual noise to the operator. So that is going to make it harder for them to differentiate a true alarm from the noise. So that is making these two peaks come closer together, essentially. So, and one of the other things that we need to take away is the criteria for where you draw the line as to what is an alarm and what is not is different for every operator. And it's typically influenced by past history. So if you are working with an operator that has been subjected to many nuisance alarms, their criteria for where they set the bar of what's a real alarm versus not could be very different from someone who is a new operator. So we need to keep that in mind. Now, how does that impact actual response and the operator's thinking? One study that was done found that if your false alarm rate, your nuisance alarm rate, is 25%, that means 1 out of every 4 alarms is not a true alarm, that is sufficient to cause the operators to stop relying on the alarm system as their means for detecting abnormal events. So 1 out of 4 is not a true alarm. There's many facilities that fall into that category or even worse. So something to think about. Another important lesson learned was that the confidence in a particular alarm, so a new alarm comes in, maybe one that the operator is not familiar with yet or hasn't seen for a while. Well, their judgment of the validity of that new alarm is influenced by all of the other alarms that exist and the number of alarms that are active. So if you have a screen that is full of stale alarms and you get a new alarm that comes in, the operator is going to be more inclined to consider that a nuisance alarm than they would be if the screen was empty of alarms. Now let's talk about ignoring of alarms, ignoring of nuisance alarms. Again, we talked about operator error and ignoring those alarms. I have to realize that that is really normal behavior. That is not essentially, that's not what we would, it's normal human behavior. And in fact, you see a good quote here on the screen from Micah Ensley, who does a lot of research into human factors and situation awareness. But if you think about what we want the operator to do, focus on the most important areas so you can drive value in the process. If they determine that there are certain areas or certain cues or certain data that is not useful, they will ignore them. That is essentially what we want them to do. We want them to focus on the most important areas, focus on the things that truly will impact the performance of the operation. And by ignoring the nuisance alarms, that's essentially what they are doing. So they are sort of doing not only what we would want them to do, but what we would expect someone to do from a human factors point of view. So what does that mean? That means you cannot get rid of nuisance alarms or change that operator behavior by discipline or training them to say you must respond. That's not the way it'll work. You need to eliminate those nuisance alarms to begin with, because as I said, it's natural human behavior to ignore them. Now, how do those nuisance alarms, how can they impact operator reliability? In the world of safety design, for layer protection analysis, where we are analyzing the barriers that we have to prevent an incident from occurring, to prevent a hazard from escalating, alarms and the operator response to them can be considered one of those layers. Needs to meet some significant criteria to do it, and many companies thus do not use alarms as formal protection layers. But as part of that analysis, that needs to be assigned a reliability. What is the likelihood that the operator is going to respond correctly or incorrectly? the reverse or the inverse, and that's called the probability of failure on demand. A typical figure of merit there is a probability of failure on demand of 0.1, which means 10% of the time the operator is going to not be able to complete the response correctly. So that sounds like a pretty nominal value, but if we think about real life scenarios and we look at the actual alarm system performance and we see that, hey, the alarm that we're counting on the operator to respond with a high reliability is actually a nuisance alarm. So let's say that alarm from the layer protection analysis, or the alarm from, that's a safety alarm, or a safety related alarm as it's called in EMUA. What if that particular alarm is a nuisance alarm? The operator is going to ignore it. So you better believe you're not going to even get the level of reliability that you thought you would, 90% reliability. And if your overall system has too many alarms or has too many nuisance alarms, that is going to impact the reliability of the operator to respond to that important alarm again as well. So if you measure your alarm system performance, which is something that you are supposed to do, and you detect that either that individual alarm is a nuisance alarm or you have many nuisance alarms in your system, then that may cause you to reevaluate the reliability of the operator's ability to respond. And if you are taking formal credit for that as part of your risk reduction, you may want to rethink that. You may find that it's not really correct or a good practice to take a high reliability for an operator if they are subjected to nuisance alarms, because that is going to introduce significant issues for expecting them to respond in a reliable fashion. So now let's talk about how we can eliminate nuisance alarms. First thing we need to do is remember what an alarm is supposed to be. Definition that's set in the IEC standard and the British standard. Alarms are relevant to the operator, needs to be understandable and actionable by the operator, needs to indicate an abnormal condition, something is wrong, and it also needs to indicate that the operator must take a corrective action, some true corrective action. One of the problems or initiators of nuisance alarms is that we are presenting things that are not truly alarms according to this definition. And by the way, the process of rationalization is to make sure that every alarm that you've configured for the operator to see meets this definition. But if you are presenting what we call here as alerts, so maybe it's an abnormal situation, but the operator doesn't need to respond, it's just for informational purposes, that is a nuisance alarm in the scheme of what are alarms. So if that is one thing that you're doing, presenting all that information to the operator through the alarm summary display, then you need to segregate those notifications. And those other non-alarm types need to be presented to the operator via a different means, different summary display, for example. But the main way that we'll address the nuisance alarms is through the rationalization process, which is a series of steps, including the first one, checking the alarm validity, determining the consequences if the operator doesn't respond, documenting the cause, corrective action, documenting the amount of time that the operator has to respond. Those are the things that we look at first to determine whether something is a real alarm or not. And if it passes that test, we continue with the rest of the rationalization process, which includes assigning the priority, the classification, reviewing the alarm limit, setting on delay, off delay, deadband. We'll talk about those. And then the last step is to define whether there's any scenarios, states or modes of the process, where the alarm either needs to be suppressed or perhaps have a different limit to act appropriately in that state. And as I mentioned earlier, we have a tool called SIL Alarm, which will guide you through the rationalization process, as I've shown here, and help you to document and capture the results for all alarms. So not just safety-related alarms, but all process alarms. So the first step in the rationalization process was to quickly check whether the alarm is valid or not based on criteria that we establish in our philosophy. If we take the criteria from the definition of an alarm, we could establish questions such as, first, does the alarm indicate a malfunction, deviation, or abnormal condition? That's a yes or no question. If we can't answer yes to that, it shouldn't be an alarm. Second, does it require a timely operator action to avoid defined consequences? Again, we need to be able to answer yes, or it is not an alarm. And here you see some other criteria as well. Is it unique? Is it the best indicator of the root cause? So let's take that validity criteria and apply that to a common situation. And we'll look at the way sump pumps are often designed, such as in the example that we looked at, the incident. So in this case, the P&ID says turn on the pump at the high level alarm and turn off the pump at the low level alarm. So it's an automatic start stop of the pump based on the level, where the set point is 85%, for example, for it to turn on. So that's the high level alarm. So let's apply what we've just talked about to analyze that high level alarm. So the first question is, does it indicate an abnormal condition? The high level in the sump that's being used to automatically turn on the pump. And the answer to that question would be no. That alarm is only really indicating that the pump has turned on as it's supposed to. Second criteria, does it require a timely operator action? What's the operator supposed to do? What do they do when that alarm occurs, when the pump turns on? Nothing. There is nothing for them to do at that point. So we've determined that this is not a valid alarm. Then we would continue with the alarm objective analysis portion of rationalization, establishing the cause, making sure it's an unexpected situation, documenting the consequence, and we're after the direct consequence, not the ultimate consequence. So what is it that the operator's response would prevent? So for this example here, the direct consequence would be the trip of the SIS rather than the explosion or chemical release that you see there. We want to document the corrective action, make sure there is something for the operator to do, or else it's not a valid alarm. And then last but not least, potentially document the confirmation. Now, those of you that have done rationalization before are probably familiar with documenting and discussing the cause, consequence, and corrective action. But I do want to talk a little bit more about the last one, confirmation, something new. What is confirmation for, or what is it? It's additional information, other process measurements that the operator could look at to determine that the alarm is real. So it's a way for them to cross-check. It's a way for them to confirm that it is not truly a nuisance alarm or a false alarm, and that it does in fact require their response. So this is a significant thing to do, or to provide them with this information as a means to wean them off of the practice of ignoring alarms. If you give them the ability via this other information to determine whether the alarm is a nuisance, a false alarm, or a real alarm, and they use that, then they will come to the correct conclusion about whether they need to respond or not. So that information can be documented during rationalization. And then what we would recommend is to present that information or make it available within the HMI via what's called an alarm response procedure. So it's the information on when this alarm occurs, what should the operator do, what's going to happen if they don't respond, what's the consequence, what are the likely causes, and how might they confirm the alarm is real. If you capture the information in our SIL alarm tool, that can be used to automatically create alarm response procedures, either in PDF format, or in some cases we can configure it in the DCS, such as here shown with an example from a Delta V system. So one of the common questions that comes up about redundant alarms, and in this scenario, redundant alarms, we're talking about both high and a high alarm for a single tag. We want to get out of the practice of having a high alarm as a backup for the high alarm in case the operator misses it, or as a redundant alarm. That's not an effective alarm management practice. So what we want to do is define the criteria for when it's appropriate to have that high alarm. So something about the two alarms, when you analyze them, high and high, or low and low, same thing, something needs to be different, either the cause, the consequence, or the corrective action, the operator response would be different in kind or degree. One of those three things needs to be different, or else the alarms are truly redundant and you don't need them both. Now, what do we mean about operator response in kind or degree? If we look at this tank level, and if we think about high-level alarms and high-level alarms and how the operator would respond, if the operator's ability to respond is fixed on just the manual valve, when the high-level alarm is triggered, the operator response could be reducing the flow. Then if that's not sufficient and the level continues to rise, when that high level alarm goes off, then the operator can close that valve completely, stopping the flow altogether. Those are two different alarms because the response is different in kind or degree. Another redundant alarm example is the cascading alarm effect, when an automatic action occurs and that creates a series of alarms, such as when we have a pump and we have alarms related to the discharge pressure or the outlet flow. If you don't do anything in your logic, it's very likely that you're going to get a low discharge pressure alarm or a low outlet flow alarm anytime the pump turns off or is stopped. But that's not a real alarm scenario. So what we want to do is to make the triggering of that low pressure alarm smarter and not just look at the value of the pressure, because that can be low on purpose when the pump is stopped, but to also incorporate reading and looking at the status of the pump itself. So we only want that low pressure alarm to be active and to go off if the pump is running, because that's when we care about it. So we can make that part of the annunciation of the alarm so that we don't just look at the pure pressure level, but we also consider in that the status of the pump, whether it's running or not. So that's redundant alarms. Now, one of the causes of nuisance alarms, particularly stale alarms, is if the alarm limit is just not set correctly. So how do you set alarm limits? Well, if you go through rationalization, you have defined what the consequence is, and then you can take that and say, well, at what point of the process, of what value of the process, of what value of the pressure, for example, would that consequence occur? And if it's a relief valve, for example, we know what that setting is, so that forms the upper bound for where we want to prevent the process from getting to. So we want to set the alarm limit in relation to that consequence and also in relation to our normal operating envelope to make sure that we're not setting the limit too close to the normal operating envelope, or else we'll certainly get chattering or nuisance alarms, and not too close to the consequence threshold, or else the operator may have insufficient time to respond. Now, as part of this analysis, if we find that the gap or the space between the consequence threshold and the normal operating envelope is too small, then maybe it doesn't even support having an alarm. So alarm set points or alarm limits can be the cause of stale alarms in some cases, and in some operations that's because the limit needs to be different depending upon the state of the process. So this is showing how in our SIL alarm tool we can capture different requirements for the priority or the limit as a function of state. So if you have a stale alarm that's based on an incorrect set point as a function of operating mode, that alarm's not going to clear until you change to a different operating mode or you dynamically change the set point. Assessing alarm deadbands and tweaking them is another key way to get rid of nuisance alarms. If we look at the picture on the left, we can see that every time the process value goes above the alarm limit, that creates an alarm event. But if you see, due to the normal up and down fluctuation in peaks, we've actually created 4 alarm events. That's a chattering alarm, 4 alarm events here on the left-hand side. The way we correct that is by implementing alarm deadband or hysteresis. Sometimes it's called hysteresis. That adds a buffer that essentially makes it so that the alarm needs to clear that amount before the state would be changed within the control system. So how does that work? If we look at an example, pressure that's scaled from 0 to 100 psig, we set the high alarm at 90 psig and we apply a deadband of 2%. So now the alarm occurs as soon as the pressure goes above 90, and any fluctuations then thereafter in the range between 88 and 90 do not cause the alarm to change state. It doesn't clear until the value drops below 88. So that's how we smooth out the fluctuation and eliminate chattering alarms. Now you have to be careful when you're applying deadband, because if you set the deadband too big or set it inappropriately, that alarm may not clear, and you may create a stale alarm just because you've set the deadband inappropriately. Interesting real-life example of operators looking at their alarm summary display, knowing what the process value is currently versus the limit, and saying, you know, we've actually gone below the limit, but the alarm is still there. Why is that? That's because of the deadband. It needs to clear that deadband. If the deadband is set incorrectly, as in too big, that alarm may not clear and it'll stay there as a stale alarm. So in this example, the operators used to go into the alarm and change the deadband from whatever it was to 0, which would cause the alarm to clear, and then they would change it back to what it was supposed to be, all in an effort to eliminate the stale alarm. So instead of changing the deadband to something more appropriate and analyzing or using other techniques, they would manually change the deadband to clear the alarm. One of those other techniques is implementing on and off delays. This is a way to delay the enunciation of the alarm, you know, till the alarm kind of makes up its mind, or the process variable makes up its mind that it wants to be an alarm. So if it's not an alarm for 10 or 15 seconds consecutively, you don't enunciate it. Off delay is essentially the reverse of that. That also helps to get rid of chattering alarms. There are recommendations in the AMUA 191 guideline. There are recommendations in the original ISA standard. I think they've been removed from the IEC standard, but typically these values are applied based on the type of process variable. But when you apply them, there are definitely things to consider. Certainly you would typically apply the deadband first, because that's the most powerful, then apply the on delay, because that will get rid of chattering and fleeting alarms. But you do need to be mindful of what on delay is. It's delaying the enunciation of the alarm to the operator. So if you have an alarm with a short response time, if you implement an on delay, you're essentially robbing the operator of response time. So you would need to be mindful of that. Off delay can also be used, less powerful, typically used when the others don't have any impact. There was a study done by the ASM, primarily for plants in the UK, that found that just by tweaking these parameters that we've talked about, we're able to reduce the alarm load on the operator by 45 to 90%. Pretty fantastic results. Another thing to keep in mind is the standards now require that the DCS provide both deadband capability and on-off delays, because that's what one would primarily use to eliminate these nuisance alarms. So as a means of helping operators to get rid of these alarms or to prevent them from seeing them, DCS must support that underlying functionality. So we're kind of wrapping up here. Benefits of rationalization. So by going through the rationalization, what does that do? Hopefully it eliminates nuisance alarms, or at least minimizes the number that the operators get, it will shift the operator's reliance on the alarm system. If they've been ignoring alarms, going through rationalization with having them participate in that process will help them see that the redundant alarms have been eliminated, which means now you got to respond the first time you get the indication, because you're not going to get a third, fourth, or fifth chance. Essentially, you want the operator's mentality to change to take each alarm individually very seriously. And that is one of the key benefits of rationalization that can occur if rationalization is done correctly and successfully, and if it includes the operators in that activity. So we want them to kind of walk away with, there's no more ignoring of alarms. You're going to have to take action when that alarm comes in, because every alarm that's left after rationalization is significant and requires their action. Now, one last thing about if there are nuisance alarms present and you haven't been able to get rid of them yet, or you can't get rid of them, not a good idea to just leave them blinking and whatever to the operator. So the modern DCSs are supposed to now include the ability to shelve alarms. This is a way to temporarily suppress the alarm from the operator. Typically, this is done by the operator, so it's under authorization and control. And what happens is the alarm disappears temporarily, goes to a different summary display, and that alarm will come back after a period of time. So the idea is, if you have a nuisance alarm, rather than making the operator deal with the nuisance alarm and put up with it, if it's a known nuisance alarm, then you can temporarily suppress it, and that removes it from the operator's view, allowing them to better concentrate. So in summary, what did we talk about? Nuisance alarms, the detriment, how they can impact the operator's performance, and the way the operator thinks about alarms. So ignoring nuisance alarms, which is what often happens, is, as we talked about, normal behavior. The only way to get rid of it, or the most effective way to change that behavior, is to get rid of the nuisance alarms. Include your operators in the rationalization process. The disciplining is not the appropriate way to change that. We want to be measuring the alarm system performance so that we can identify what nuisance alarms exist, and then apply the mediation techniques that we talked about. Perform the alarm rationalization. Get rid of alarms that don't belong. As part of that rationalization, identify how the operator can confirm the alarm is real. Apply deadbands and on-off delays to get rid of chattering alarms. Evaluate the alarm limit, the alarm set point. Doesn't need to be a function of the process state. Is it set correctly in relation to the consequence threshold? So we want to make sure that alarm set points are set correctly. And then for the scenario where you have not been able to truly eliminate all nuisance alarms, which we said may not be possible, we want to prevent, or we want to provide the operator with the ability to temporarily suppress the alarm, and that's called shelving. So, and one final takeaway for that is, if you have nuisance alarm issues and you are taking credit either qualitatively or quantitatively for operator response to alarms, you may want to change that or revise that or reduce that based on the fact that nuisance alarms can impact the operator's reliability. So it all goes together. That's how we bring together the worlds of alarm management and safety. So I know that we are a couple minutes over. I apologize for that. Unfortunately, we're not going to have time to answer questions. But if you have questions, please submit them, and we'll take a look at them after the seminar and send out the answers. Now, I did want to just put in a plug for a couple of alarm management classes that we'll be having in the UK in July in Warwick. There'll be a 2-day training class on how to do alarm rationalization. So we saw a little bit about what the process was, but a lot more detail about alarm rationalization and how you use the SIL alarm tool. And then a 1-day class that provides a high-level overview of alarm management practices and principles according to the standards and best practices and guidelines that exist. If you want more information on any of those training classes, please feel free to contact Allie Coles. Her email is shown there below. So on that note, I will say thank you very much for attending. And again, if you have questions or feedback at all, please submit that via the question box, and we will get back to you with those answers. So after this presentation is done, we will send out an email that gives you a link to the slides, to the recording, and also to that Lego nuisance alarm video, which I would encourage you to check out. So on that note, I'll say thank you and have a good day.